Hi, this is Ishan Bhatt from MDX Tutors. So today we are going to understand what is energy and what is energy of a system. We are going to define a few terms, and those terms will be very essential. Those will work as the basic skeleton, the basic structure to understand energy much deeper sense and to understand the various aspects of energy of a physical system. So energy in this class we will going to understand majorly. Let me draw an overview. Energy of a system. What is a system? A definition of a system, because understanding the prerequisites before going much deeper into energy is very important. Now, if we have defined this particular system, what are the conservation laws? The conservation laws which are necessary for us to understand energy of a system. So these conservation laws, there are pretty a lot of conservation laws. Law of conservation of momentum, law of conservation of angular momentum, law of conservation of energy. So our focus here will be on this energy conservation laws. And after finally understanding these conservation laws, we will dwell more into the topic of the various types of energies. Understanding energy is one thing, but in real application, what are the various types of energies? And we will going to investigate a few of their mathematical description. So this will be the overview of today's lecture. Now, before understanding what energy is, let us first try to understand what a system is. A system is composed of two things. One is the object on which the recording is being done, object on which the experiments are being performed and some reading is done. And then what is its interaction of this object with the environment? Now, the relation of an object and with an environment is very important to understand. Now, let me just give you a small example, a very basic example, in which we have a cliff, and from the cliff, there is a person who is going to drop a ball. Very simple. Now, this ball which is going to come towards the surface of the earth, it is not just that we are going to understand the interactions of the different things which are going to happen with the ball. We are also going to understand what are the various types of interactions which are happening with the environment acting on the ball. So a few forces, let's say, if we are trying to understand what are the forces which are acting on the ball, the few forces which act are the weight of the object. Then we can always have some viscosity, air resistance, which is offered by air or any other fluid, which is acting opposite to the direction of the motion of the ball. We can even have some interactions of the particulates which are present always in the air, resistance through them. We can even have, let's say, some electrostatic or conducting charges and their repulsions, if let's say this is a conductor. So there are various types of interactions of the object with the environment. So we need to study both the object as well as the environment to understand what the energy of a system is. Now, a very common and very important term which comes in our understanding of the system is what is a closed system. What is a closed system? A system in which all the things that you want to understand are self-satisfied inside that particular system, and there is no point in understanding the various interactions which are happening outside those particular system. That is a closed system. Let's say we are having a thermos. Now in this thermos we have some hot water kept. This hot water is constantly trying to radiate its heat outside the bottle, but because this, of course, it's not a perfect thermos, But let's say it's a near perfect thermos, and that thermos will not allow heat transfer to go outside thermos. That means if our subject of understanding is heat, what is the heat which is acting on the system? This heat is not being transferred outside the system. So the water which is present here inside the thermos, that is our object. The study is going to be on the object. And then we have this container, this bottle, this thermos, which is the environment. And study of this environment and object composed so that no interaction is happening of the system with outside environment, that is a closed system. So in majority all of the cases that we are going to learn in the further sessions are going to be closed systems, and understanding these closed systems are important. So systems having no net change in their total energy, when energy transfers are always happening within them, that is a closed system. Now we need to understand what is this conservation of energy. Conservation of energy. So there are various methods in understanding and defining this law of conservation of energy. It's a law. That means it is a fixed principle. It is valid at all times, in all cases, in all spaces. So we do not need to worry much that is this applicable in this condition or not. No, it's a law. It's a conservation law. It has to apply all throughout your experiments. So in the conservation of energy law, this law states that no energy can be transferred no energy can be created or destroyed. If no energy can be created or not, or can it be destroyed, then what can happen with that energy? The only thing that can happen with the energy is that energy can either be retained in the system or it can be transferred to the system or transferred to the other parts of the environment. So energy can never be created nor be destroyed in any case, because the net energy of a system is always kept constant. But we are having here that this energy can be transferred or it can be retained into the system. Now let me give you a brief example, a very common example, in which we have a ground, a surface, and then there are two balls which are going to interact with each other. So this ball is trying to come in from this direction, from plus x towards the minus x direction, and this ball towards the plus x direction, and definitely they are going to have some interaction. When they are going to touch with each other, there will be a collision, and then we will see that after this collision, this left ball will go in the opposite direction and the right ball also in the opposite direction. Now let's say we have considered that this is a system in which this is a ball A and this is the ball B. So A and B combined will give you the system. And this is also a closed system. So whatever energy was here in this ball, let's say both of their masses are same. This is having mass m, this is also having mass m. So if this is having velocity of, let's say, 5 meters per second and this is having velocity of 10 meters per second, we can carry out all the equations and we will be able to understand that when the masses are same, the velocities or the speeds are being interchanged. So this velocity, the velocity of the left object will be 10 meters per second in the opposite direction, and this will be 5 meters per second in the opposite direction. So in this combined system, we can see that the net energy of this system, later on we will understand how to evaluate this energy, but no energy can be created or it can be destroyed. This is the law of conservation of energy. Now, after understanding this conservation law, we are having some prerequisite knowledge to go further into the topic of what are the various types of energies. So there are lots and lots of types of energies, but we are going to focus majority on only 3 to 4 types of energies. We can have chemical energy, right? Chemical energy is in the form of ions that are being stored inside the chemicals. Let's say a pencil cell or a battery. So example being a battery. In the battery, that chemical cell is then converted into electrical energy. So the next being electrical energy. Let's say electricity. Then there is also thermal energy, radiated in the form of heat. There can even be nuclear energy which is radiated in the form when two subatomic particles or atomic particles like electrons or neutrons or protons, these also through nuclear fission, through nuclear fusion, radiate a lot, immense amount of energy, and that is nuclear energy. So all these various types of energies are there, and you will see that even in this case battery, this battery, when it is getting discharged, so this is the battery connected to a bulb, let's say. So this chemical energy is getting transferred and being converted to electrical energy. And this electrical energy is in fact important to turn this light bulb on. So all these energies are actually same. These are different types of energy, but it's the same energy, and this is being getting transferred from one form into another form. But we are not going to understand much about these types of energies. What we are focused on are a few types. For example, kinetic energy, potential energy, and total energy. These are something which we can evaluate also. So when an object is in motion, which corresponds to the fact that object has some non-zero velocity. Object having non-zero velocity, that means v, if v is the velocity, okay, let's just define the magnitude of the velocity. So v is non-zero. So v is non-zero. So then we define this kinetic energy. There are various notations for that. Some define it as ek as kinetic energy, some even define it just by k, some define it by t. That doesn't depend what notation you use, but this kinetic energy is equal to half times mass of the object which you are concerned with times what is the velocity of that object squared. So half mv squared. This is the kinetic energy of the object. The potential energy is what energy does it hold? What energy does it hold So there is a lot of potential, right? There's a lot of potential in some object to showcase its energy, but it is in its latent form. It is not being shown, but it's still there. For example, let's say we have a catapult, or let's say a rubber band. So in this rubber band, we are going to stretch this in from the opposite ends and going to stretch it much so that it lengthens in its size. So this stretching also, we cannot see that there is much of motion inside this rubber band, but we can see that there is some hidden amount of energy, some latent energy which is present in the elastic, as stored as elastic energy in this rubber band. And this energy, which let's say we are defining as at PE, this is equal to half times K times x squared, which is looks very common to this. So for example, let's say we have a ball which is moving with mass m and velocity v. So it is moving from here to here and having some displacement. So the kinetic energy of this ball is going to be half mv squared. Okay. Now this potential energy, which is in the form of half kx squared, this k is like the potential energy constant. So for example, let's say we have a spring. A spring, when it is being compressed or is being expanded in its direction, it will have some form of potential energy which will be stored, which is dependent on the how much length you are changing. This x displacement from its mean equilibrium position, how much you are changing in that, the square of that is dependent, the potential energy is dependent on the square of that. So potential energy is this half kx squared. And the total energy is nothing but this kinetic energy added with this potential energy. Okay. So an important example, let's say we can give of a ball which is going to let's say it's in x direction, and there is a spring which is just attached to it. So we have already compressed this string in x displacement and compressed it. So the amount of potential energy which was there in this system, right now the system is both the spring and the sphere. So the potential energy which was here present earlier was half kx squared. K is the spring constant. It's a constant of the spring which is dependent on the material of the spring. And now that we have released this spring, we will see that the ball of the object, which is the ball here, this ball was earlier in having zero velocity. Now because of the force which is going to be imparted from this spring towards to the ball, this potential energy of the spring will be equal to half mv squared, which is the kinetic energy of the ball. So this energy transfer has taken place. Notice that conservation of law of conservation of energy still holds true in this case, because the entire system is composed of the spring as well as the ball. So potential energy plus kinetic energy, that is the total energy of the system before and after, will be equal. So that is giving us these expressions. A very general few things which I would like to mention is the unit of this energy is joule. There are several other units also, but this is the SI unit, and knowing this is also important. So maybe next class we will try to do some more examples and those examples along with the numerical values. Thank you for joining.